Mhm.
Namaskar, hello and welcome to the day two of Know the Nobels Forum 2023. Today is 3rd of October and the Royal Swedish Academy of Sciences has declared the Nobel Prizes in Physics to three Nobel laureates, out of which two are males and one is female. The Nobel Physics Prize for the year 2023 has been conferred upon the triumvirate of Pierre Agostini, Ferenc Krauss, and Annie L. Heulier. And the Nobel phenomena which has been discovered, which has been awarded this Nobel Prize is for the experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. So quite a verbose aspect. From tomorrow, the World Space Week would be commencing 4th to 10th of October every year. The Space Week gets commemorated where the distances are measured in light years. So the Nobel Physics Prize for the year 2023 has been given to a phenomena. Uh, it is around attosecond physics, and attosecond physics, if in scientific notation, if we take it, it is 10 raised to the power minus 18 of a second. Now, what is it all about? We would just capture in today's Know the Nobel forum. And yesterday, when the Nobel Prizes announcement started happening, so it was the day for medicine and physiology, whereby the modified mRNAs were awarded out there. So today, physics, it is at the subatomic level to measure the electron dynamics. So this is the phenomena which the Nobel Committee has chosen to uh, to uh, uh, chosen to recognize for the year 2023. And as Alfred Nobel said in his famous will, that the prizes have to go to those who in the preceding year have conferred the greatest benefit to mankind. So how this attosecond physics is going to benefit the mankind in a phenomenal way, we will be just coming through it. We will be double clicking of this Nobel Prize winning phenomena. So in the scientific terminology, it is considered to be, attosecond is considered to be a quintillionth of a second. Now, quintillionth is 10 raised to the power minus 18. But what in the human sense? It is an attosecond is to a second, like a second is to the life of the universe. So in a simple term, the entire life of the universe, as is known in the scientific fields, those many seconds are there. Those many attoseconds are there in 1 second, as those many seconds are there in the life of the universe. So you can just understand that the macro and the micro are just working almost on a similar scale. One is at the mammoth external level, the other is at the subatomic particle level. So these three Nobel laureates, will come to it, they gave the humanity the new tools for exploring the world of electrons inside atoms. Now we are going at a subatomic level. So they have given the tools for exploring the world of electrons inside atoms and molecules. And why it is so very important, we'll just unravel it in a short while from now. And they have demonstrated a practical way to create extremely short pulses of light that can be used to measure the rapid processes in which electrons move or change energy. So moving on, so what are the fast moving events we all observe? Fast moving events flow into each other when perceived by humans. The moment we see a film that consists of still images, it is perceived as a continual movement. And if we want to investigate really brief events, very, very short events, we need a special technology. In the world of electrons, changes occur in a few tenths of an attosecond. And an attosecond is so short, so short, that there are as many in 1 second as there have been seconds since the birth of the universe. So this is what the power of this Nobel Prize winning physics award for the year 2023. And the Nobel laureates, the triumvirate, one female, Madam Annie Lee Hewler, she laid the theoretical foundations for the creation of short pulses of attoseconds. And these two gentlemen, the scientists, will come to their introductions further. Pierre Agostini and Farang Krauss, they really set out the experiments which produced attosecond pulses. So the laureates' experiments have produced pulses of light so short that they are measured in attoseconds, thus demonstrating that these pulses can be used to provide images of processes inside atoms and molecules. We will understand, like, if we have to measure something, we need the tools faster or shorter or more effective than the object what we are measuring. So this is the physical phenomena we are trying to understand in this Know the Nobels Forum 2023 on physics. Now, just coming to the a natural phenomena, a tiny hummingbird, as we see, it can beat its wings 80 times per second. But we are only able to perceive this as a whirring sound or a blurred movement. For the human senses, rapid movements blur together, and extremely short events, they are impossible to observe by the naked human eye. We need to use technological tricks, actually, to capture or depict these very, very brief instants. So high-speed photography, as we have seen across Discovery channels or Discovery Science, how high-speed photography or strobe lighting, it makes it possible to capture detailed images of fleeting phenomena. A highly focused photograph of a hummingbird in flight requires an exposure time that is much shorter than a single wing beat. The shutter of the camera has to probably capture it in a shorter duration of what the hummingbird flaps its wings. So the faster the event, the faster the picture needs to be taken if it is to capture the instant. So this is the fundamental premise. If we have to capture a event which is very, very fast. So the picture, if we have to measure it, if we have to image it, so the picture needs to be taken, has to be faster than that phenomena which is happening. So the same principle applies to all the methods used to measure or depict rapid processes. So any measurement must be done more quickly than the time it takes for the system being studied to undergo noticeable change. So otherwise the result remains vague. So this year's 2023 Nobel laureates have conducted experiments that demonstrate a method for producing pulses of light that are brief enough to capture images of processes inside atoms and molecules. Since the discovery of the electron, the classical physics, what we have been studying all through, the idea, the plum pudding model and the various other models which we have studied, the scientists, the physicists, they have had the vision, the aspiration, the ambition to study as to how electrons actually work inside. It's an electronic age. We call it electronic age because it's all because of the phenomena of the electrons and the entire LEDs, the entire scientific advances, been computing or been a lot of other spaces. It's the electron phenomena. So scientists wanted to capture the movement of the electrons, and that's why the need of this attosecond pulses was perhaps brought about, was felt all through. And we have with us Dr. Surbhi, who is sitting in the backdrop of a lighting universe. So, Dr. Surbhi, I would just like to request you to take on this next slide as to what are these atomic movements. And mind you, friends, viewers, that these attosecond pulses are going to have a phenomenal impact in medical diagnostics. This is one of the biggest implications, because human body healthcare, the use of these advanced technology in the domain of healthcare is going to be one of the biggest applications which the Nobel Committee and the other scientists are looking at it. So over to Dr. Surbhi to take on this slide. Yeah.
Yeah. Am I audible?
Yeah, loud and clear, please.
Yeah. So, in sciences, we talk about precision, nanoseconds, and now we're talking of the attosecond. So precision, and the more minuscule you go, the more accurate and the more pointed you are. So what we are saying here is that the atom's natural time scale is incredibly short. In a molecule, atoms can move and turn in millions of billionth of a second, femtoseconds. These movements can be studied with the very shortest pulses that can be produced with a laser. But when entire atoms move, the time scale is determined by their large and heavy nuclei, which are extremely slow compared to light and nimble electrons. When electrons move inside atoms or molecules, they do it so quickly that changes are blurred out in a femtosecond. In the world of electrons, positions and energies change at speeds of between 1 and a few hundred attoseconds, where an attosecond is 1 billionth of a billionth of a second. Now, this is some precision, some, what we say, miniaturization or micro digging. An attosecond is so short that the number of them in 1 second is the same as the number of seconds that have elapsed. Just imagine, since the universe came into existence 13.8 billion years ago. On a more relatable scale, we can imagine a flash of light being sent from one end of a room to the opposite wall. This takes 10 billion attoseconds. So this is about the atomic movements, and it gives us the idea of the scale of the attosecond.
So the difference, what I would say the biggest impact on the humankind, that in order to study the subatomic particles, nuclei, as we all know, it contains the major mass of an atom. So femtosecond pulses were okay. Lasers are in that duration. So 1000 attoseconds is equal to 1 femtosecond. That is the kind of order we are talking about. But when it comes to the very light and nimble electrons, you need a pulse which is even much shorter than a femtosecond pulse. So that is the difference. And here we would like to recollect the de Broglie's principle, the electron microscope discovery, all those physics what we have studied, what we have gone through, that the de Broglie's uncertainty principles, that you cannot measure deterministically the mass and the velocity and the momentum of a subatomic particle. So the physics is getting further granular. They said that when a photon of light gets incident on a atomic particle, either so you cannot determine both the phenomena in one go. So here the aspiration and the ambition is to measure, is to picture the electron movements and how these scientists did it. That is the story which will unravel in a short while ago. See, physics is phenomenal. The entire cosmic reality at the most, I would say, concrete level, it is physics all around. Now, when we dig deeper, we go into the chemistry of things. And then yesterday we saw when the Nobel Prize of medicine was given, it had a biochemist and an immunologist coming together. So it is quite an intertwined space, the intertwined of all the sciences, the physics, chemistry, biology, and obviously mathematics. It's all about billionth of a billionth. So without the scientific notation, so the PCMB space gets so intertwined out here. And also for the young students and for the contestants of the Nobels contest, which Rethink India organizes every year, the whole idea is to appreciate what physics is actually, what are the scientific discoveries which lead to technological advances. So that is, you can understand the STEAM compact, the science, technology, engineering, arts, mathematics, the STEAM we talk about, the buzzword out there. So these scientific discoveries, they lead to technological breakthroughs, and then they are engineered upon to create systems, processes, products for the welfare of the humankind. Dr. Surbhi being a medico, how the laser surgery has become so very ubiquitous, and as we will see how Madam Annie Le Hewlett, she used laser beams to create, to lay the theoretical foundations that using the laser beams, infrared laser, we can create the attosecond pulses. So laser precision, it has a huge implication in the medical sciences, the surgery without incisions, without cutting, how getting into the veins or the arteries, how, because human body is
absolutely, absolutely. I would just like to come in here and add here that laser surgeries, be it crypto laser, YAG laser, they're all very, very highly intense pulses of quantas of energy, which are given. What are the parameters is the time period in which the laser is emitted and the impact it creates. So the time and the power combination creates that particular impact. So what we're talking about, the attosecond and the laser component, is very, very pertinent in the medical sciences too.
So the inherent objective behind this Know the Nobels forum is like to attune the student of sciences, the medical sciences, the physics, the chemistry, the three fundamental ones, and correlate with the curriculum what they undergo, that this is the zenith of it all. This is the epitome of it all. So there are two parts of Know the Nobels contest. One is the personalities behind it, the scientists behind it, their lifelong pursuit, which leads the persistence, because experimentation is not so easy aspect. Decades and decades of perseverance and sustained work leads to Nobel Prize winning phenomena. So one is the personalities, the attitude of theirs, their entire academic careers, we get to know about it. And secondly, obviously, the Nobel phenomena, which is laid on the foundations, what we know and what we intend to explore, what the breakthroughs happen in science. And at times, the breakthroughs are just very incremental, which we at times take for granted, but at times the breakthroughs are really phenomenal. So that is the appreciation part of it. We want to evoke by way of this Know the Nobels forum activities. Moving forward now, again, just trying to give you a graphical. These are all graphics coming from the Nobel website. They have official press releases. We really thank the Nobel Foundation to really go to such an extra mile to explain these very intricate and top-notch scientific phenomena in such a layman's term. This is a very lovely part, even if you are not a student of science. A Nobel Prize goes to even the politicians or the peace activists, the organizations working all around that way. It also goes to literary figures, and also after a while, the Nobel Prizes for economics have also been instituted. So humanities and sciences, they both have been intertwined so very well. So if you say what is an attosecond on this graphical scale, so heartbeat, again, a medical motive has come, and I would now bring in Dr. Surbi because as we are moving forward after, especially after the COVID pandemic, the entire focus of sciences, the entire focus of technological breakthroughs has gone to the human health. So that is perhaps the illustrators, the Johan Jansted from the Royal Swedish Academy of Sciences has chosen the motive of heartbeat. We all have a heart. So in a heartbeat, we say. So just Dr. Suri would explain it further.
So, we know a minute has 60 seconds and a normal heartbeat is 72 beats per minute. So, which means that per minute in 60 seconds, almost every second, there is one heartbeat. That's why it's saying heartbeat 1 second. So, this is a good comparison, because when we say tachycardia, the heartbeat is increasing. Bradycardia, the heartbeat is reducing. And attosecond, compared to the age of the universe and heartbeat. So these are comparative really to give the entire vistas of the time universe.
So this is like billionth of a second. So the more granular we go on this scale, ये इतना ही छोटा है, जितना the age of the universe उतना बड़ा है. So this is the classical symmetry of cosmic existence, that the activity which is happening at such a subatomic level, it is working in such a scale, the scale of time, the attosecond and the age of the universe. It is in time, in terms of we say the distance equivalent with respect to the human existence. So it is one of the other purposes is to get in awe and reverence about this cosmic creation at large, the infinitum of the universe. It shows us, it takes us beyond our petty existence, whatever we do it, ki pani kera budbuda or asmanas ki jat. So in our philosophical renditions, our philosophers over the period of time, they have expressed this same phenomena in their poems and couplets and whatnot. So, so a femtosecond, actually, it was regarded as the limit for the flashes of light it was possible to produce. That was the benchmark to an extent. Improving existing technology was not enough to see processes occurring on the amazingly brief timescales of electrons. As we told, a femtosecond is equal to 1000 attoseconds. So you had to go 1000 level further. So femtosecond, it was all possible, but existing technologies were not making it happen. So something entirely new was required. And this year's 2023 Nobel laureates, they conducted experiments that opened up the new research in the field of attosecond physics. So astrophysics is the physics of the astronomical levels, and the attosecond physics, perhaps these new coinages would come in our common parlance shortly. So this impression is so very important, and this comparison with a human heartbeat is so very lovely that it impresses upon the importance of attosecond out here. So now, lo and behold, the first Nobel laureate, and the feminine one, and the one who really who really laid the theoretical foundations of this entire discovery, this entire outcome. And before we move on, Nobel Prize is such a coveted prize in terms of prestige. But then people ask, what is the moolah associated with it? So the Alfred Nobel Foundation, which gives it, they give us every Nobel Prize is around 11 million Swedish kronor. It's a prize from Sweden. Their kronors, and 1 Swedish kronor is equal to 7.49 Indian rupees as per the current exchange rates. तो लगभग अगर हम कहें, we just said 7.5 crore, 7.7 crore Indian rupees is the total quantum of the Nobel Prize. Now, in the age of unicorns and deca unicorns and all kind of the startup valuations we are listening all through, not a big amount. It's just an amount, 7.5 crore might be a annual salary of a middle-level executive in a Fortune 500 corporation. Nothing so big about it. But yes, the prestige associated with these Nobel Prizes is phenomenal. And when Nobel Prizes are generally not given more than 3 people, and then the division happens differently. So this time 1/3, 1/3, 1/3. So lagbhag 2.5 crore rupiah, Indian rupees, if we just compute it, it goes to all 3 Nobel laureates. So N. Le Huller, she was born in 1958 in Paris, France. She did her PhD in 1986 from University Pierre and Marie Curie, Paris. Marie Curie, Marie Curie, Madame Curie, the lone Nobel laureate who was honored twice, once in physics, once in chemistry. So she comes from that French tradition, illustrious French tradition of scientific investigation. And she's currently a professor at the Lund University, Sweden. So in 1987, there's a term you can see on the screen, overtones of light. So language gets refined by the scientific discoveries also. In the musical space, Dr. Surbi being a musician herself, the tones, the overtones, hypertones. But then when it comes to, I would say, light or any wave for that matter, the overtones of light is a scientific phenomena which has been discovered out there. So Madame Annie Huller discovered that many different overtones of light arose when she transmitted infrared laser light through a Nobel gas. Now you see the interplay of physics and chemistry. Nobel gas, we study in the chemistry, which are the inert gases, the noble gases, which have their outer, I would say, the electron configuration quite well in place. We all have an idea about it. So it is something like when we let a beam of light pass through a prism. So the light gets scattered and we see all the colors coming out of it. So when she transmitted an infrared laser light through a Nobel gas, many different overtones of light. Now, what are overtones of light? We will see it graphically as well. So it happened. So this has to be understood. Now, each overtone is a light wave with a given number of cycles for each cycle in the laser light. So the laser light is perhaps broken down into further smaller beams as we are. This is what she intends to put it across. And they are caused by the laser light interacting with the atoms in the gas. It gives some electrons extra energy that is then emitted as light. So Anne Lee Huller has continued to explore this phenomena, laying the ground for subsequent breakthroughs. And yesterday also, when we saw the Nobel Prize in medicine, the theoretical foundations by Madam
Carico.
Yeah, the theoretical foundations which were created by, just a moment, yeah, Madam Kathleen Carico. That
Carico,
actually led Drew Weissman and all to create that mRNA nucleotide movements out there. So there is quite a beautiful interplay between all the sciences. Yes, when you have to go deeper, you have to segment them all across. So this is the, in a nutshell, this is what it says. We will go a bit deeper, what these overtones are all about. So shorter pulses with the help of high overtones. This is the phenomena which Ma'am Anne Le Huillier discovered. She laid the theoretical foundation. So light, as we all know, it consists of waves. Dr. Surbi, you can perhaps take this slide. Yeah.
Yeah. So light consists of waves, vibrations in electrical and magnetic fields that move through a vacuum faster than anything else. These are different wavelengths equivalent to different colors. We know that red light has a wavelength of about, for example, 700 nanometers, 1/100th the width of a hair.
So again, a
And
medical intervention. They are comparing with a human existence. Ki take your hair and 1/100th of that width will constitute the wavelength of light. Yeah.
And it cycles at about 430,000 billion times per second. We can think of the shortest possible pulse of light as the length of a single period in the light wave, the cycle where it swings up to a peak, down to a trough, and back to its starting point. In this case, the wavelength used in ordinary laser systems are never able to get below a femtosecond. So in the 1980s, this was regarded as a hard limit for the shortest possible bursts of light. So a
So
femtosecond.
here we have heard about the term frequency. Frequency and wavelength, we know they are inversely proportional. And just see the way Nobel laureates have put it across, that the cycles, frequency is depicted as cycles because it's pulsating. It goes up, goes to its starting point and then goes down. The crest and the trough, the sinusoidal cycles, the waveform might be different, but this is the core principle. So 430,000 billion times per second. It pulsates with this speed. This is the frequency. So in physics, it's very important when you go to the theoretical physics or to the applied physics, feeling physics is so very important. That's why so much of examples have been put across out here. So femtosecond was considered to be the hard limit till 1980s. Like yesterday medicine, the hard limit was that if a mRNA has to go, in the vaccine part, there were two core questions which remained as a scientific riddle for a long time. The autoimmune responses, the inflammation part, and the quantum of protein which was created by the insertion of that mRNA was not adequate. And when they changed the bases, the nucleoside basis of the mRNA, that trick happened. So that's what Madam Anne Le Huillier, she tried to make this scientific discovery, that how to break this femtosecond barrier. People have been working on this for a long period of time, but how to break this barrier? So this was the core scientific discovery which was made. So the mathematics that describes waves, it demonstrates that any waveform can be built if enough waves of the right sizes, wavelengths and amplitudes are used. The trick to attosecond pulse is that it is possible to make shorter pulses by combining more and shorter wavelength. So it was a kind of a synthesis which they made. We will just see it through crossing the femtosecond barrier, the natural barrier of femtoseconds which was existing. So observing electrons' movement on an atomic scale, it requires, we all know the simile that the size of a nucleus in a football ka maidan and a small football kept at the center. So that is the atomic structure. Nucleus is at the center and the whole football ka field is the larger. So electrons are orbiting all around that nucleus. So in order to study those nucleus, we need attosecond pulses to read those light and fimble ones. So short enough pulses of light, which means combining short waves of many different wavelengths. So to add new wavelengths to light, more than just a laser is necessary. To have laser is multiple things coming together. So the key to assessing the briefest instant ever studied is a phenomena that arises when laser light passes through a gas. So the light interacts with its atoms and causes overtones. So like the light emitting diodes, we all understand that photon emitting diodes, a lot of phenomena out there, but this is further deeper. So light interacts with its atoms and causes overtones, waves that complete a number of entire cycles for each cycle in the original wave. We can compare this to the overtones that give us sound, its particular character, allowing us to hear the difference between the same note played on a guitar and a piano. So taking it forward in a graphical format, like this is a tone, this is a guitar string. So one overtone is like, okay, half of it. It pulsates half. Second overtone is, okay, it's 3 times. The overtone 3 is 4 times. So Anne Hewler and her colleagues at a French laboratory, they were able to produce and demonstrate overtones. These are the overtones using an infrared laser beam that was transmitted through a noble gas. The infrared light caused more and stronger overtones than the laser with shorter wavelengths that had been used in previous experiments. So infrared light, it caused more and stronger overloads. And in this experiment, many overtones of about the same light intensity were observed. So different wavelengths, we needed smaller pulses. So overtones have several cycles for each cycle in the fundamental tone. So it's mapping exactly, like the size is the same. Overtone is a sub multiplier. It is cycling at a faster rate, but then it matches it nicely. So this is the physical aspect, and overtones work the same way as the light wave. So in a series of articles, Lee Hewler continued to explore this effect during the 1990s. Again, this phenomena, the foundations of it were laid in the 1990s. Most of us were not perhaps born out there, and the Nobel Prize is coming in 2023. So around 30 years. This is the usual time, 30 or so years. And her results contributed to the theoretical understanding of this phenomena, laying the foundation of the next experimental breakthrough. So this was the theoretical foundation she laid, did some smaller experiments, but then the real experimental breakthrough to produce attosecond pulses, this was done by the other two Nobel laureates. We'll come to it very shortly. So how it happens, this is a lovely graphic again from the Nobel website, the Nobel Committee. So hota kaise hai ye? So as you can see, that this is the nucleus. An electron that is bound to an atom's nucleus, it cannot normally leave its atom. It does not have enough energy to lift itself out of the well created by the atom's electrical field. It is bound to it. We all know about it, basic. Now this is the laser beam which is passing through a Nobel gas. So the atom's field gets distorted when it is affected by the laser pulse. So the laser pulse, it distorts the atomic field. So when the electron is only held by a narrow barrier, quantum mechanics allow it to tunnel out and escape, like an ostrich taking its neck out. So it allows it to escape to a while. So this free electron is still affected by the laser field and gains some extra energy. And when the field turns and changes direction, laser keeps on modulating, its direction keeps on changing. So the electron gets pulled back in the direction it came from, towards the nucleus, towards its atomic field out here. So to reattach to the atom's nucleus, because that is the stable equilibrium which the electron wants to come up to, So the electron must get rid itself of the extra energy it gained during its journey. So the law of energy conservation comes over here. We all have been studying about the photovoltaic effects, photoelectronic effects in our rudimentary senior secondary level physics. So this is emitted as an ultraviolet flash, the wavelength of which is linked to that of the laser field. This is what the overtone is all about. So this field, this wavelength would be a perfect multiple of the laser wavelength what is coming through. That is the physical part of it all. So and differs depending on how far the electron moved. Jitna dur electron gaya, so it shed off that photon. And this is how the wavelengths got created. The smaller pulses got created. This phenomena is the contribution of Madame N. Le Euler. She did basic experiments and laid the theoretical foundations to create these pulses of eta-seconds. That is what it's all about. So escaping electrons, they create overtones. That is what, like we say, light emitting diodes. So we all know that electrons go from one stage to the other stage, and when they drop back, they emit a photon. That's how we see all the LED bulbs, which have now taken all our creation out here. So escaping electrons also create overtones. That is what this Nobel Prize winning phenomena is all about. So when laser light enters the gas and affects its atom, see, physics, in order to understand, you have to go iterative. The same thing is written out here, but in order to create your own knowledge graph, the understanding part of it all, feeling the physics part of it all, you have to go back and forth like a pendulum. That's how the knowledge graphs builds up, and that remains a prominent focus at Rethink India to make learning more enjoyable. And even the abstruse topics, even the complex ones, can be comprehended easily in this fashion. So the same phenomena what we saw in the graphic, we are trying to explain again in a written word, that when the laser light enters the gas and affects its atoms, it causes electromagnetic vibrations that distort the electrical field holding the electrons around the atomic nucleus. We are seeing it, yeah? And the electrons can then escape from the atoms. However, the light's electrical field vibrates continuously. And when it changes direction, a loose electron may rush back to its atom's nucleus. During the electron's excursion, it collected lots of extra energy from the laser light's electrical field to reattach to the nucleus, and it must release its excess energy as a pulse of light. This excursion of the electron, the escape, the momentary escape, the short escape of the electron from the hold of its nucleus, due to the direction changing infrared laser, it creates the short pulse. This is the trick what these Nobel laureates have leveraged to create eta-second pulses. So these light pulses from the electrons are what create the overtones that appear in the experiment. So overtones are the wavelengths which are a fraction of but they are the complete multiples of them. So we have seen that overtones, either they are 2, 3, 4, these overtones will complete to the whole wavelength. So femtosecond we had achieved, but 1/1000 it can be achieved by it, and this phenomena further goes on. We'll come to it. So light's energy is associated with its wavelength. Its energy is associated with its wavelength. The energy in the emitted overtones is equivalent to the ultraviolet light, which has shorter wavelengths than the light visible to the human eye. Because the energy comes from the laser light's vibrations, the overtones vibration will be elegantly proportional to the wavelength of the original laser pulse. The result of the light's interaction with many different atoms is different light waves with a set of specific wavelengths. So this is the principle which has been enunciated. But the core thing is, once these overtones exist, now you will all wonder that, oh, similar discoveries have been going on since times immemorial. Passing a light through a gas has revealed the scientist all these subatomic, I would say, notions, and the same methodologies, the same paradigm goes on, but then science is getting refiner. The requirements are becoming more and more what was done in 1960s. So 1990s, the phenomena, the aspiration, and the eye became different. So now this is the lovely part of it all. It's like a cocktail. The overtone cocktail, we will just see to it how these various overtones interact, and then they create attosecond pulses. Let's come to that. So they interact with each other. Once these overtones exist, they interact with each other. The light becomes more intense when the light waves peak coincide, but becomes less intense when the peak in one cycle coincides with the trough of the other. So in the right circumstances, the overtones coincide so that a series of pulses of ultraviolet light occur. And when each pulse is a few hundred attoseconds long. This is obtuse, we'll appreciate it in the next slide. So physicists understood the theory behind this in the 1990s, but the breakthrough is in actually identifying and testing the pulses. It occurred only in 2001. So it takes so much of time to understand a complex scientific phenomena. So this is what we were talking about. The world of electrons is explored with the shortest of the light pulses. So before we come to the graphical description of this complex stuff, let's meet the other two Nobel laureates, Pierre Agostini. He did his PhD in 1968 from Aix-Marseille University, France. He's a professor at the Ohio State University, Columbus, USA currently. And Ferenc Krauss, he was born in 1962, in Moore, PhD in 1991. So see the age difference. So Pierre Agostini, PhD in 1968, he's quite young that way. His PhD came only in 1991, born in 1962. And from Vienna University of Technology, Austria. And he's a director at the Max Planck Institute of Quantum Optics, Garching, and professor at Ludwig Maximilians University at Munich, Germany. So in 2001, so this is what it is, that this phenomena 1990s, Madam Anne Leader had already brought about, but breakthrough identifying and testing came in 2001. So Pierre Agostini succeeded in producing and investigating a series of consecutive light pulses, in which each pulse lasted just 250 attoseconds. At the same time, parallelly, because this is Germany, this is France, so you know the entire geopolitics of Europe. Still, European Union is there, but still the national pride, the competition, the intra-European competition exists. So this was done parallelly. At many of the times, the scientists converge, but then Nobel Committee, they try to bring together, they try to weave a narrative. Okay, this lady did so much of foundational theoretical work, which this theory led to this experimental part. And these two gentlemen, who are almost their age is the year 68, he got his PhD. Ferenc Krause was just a boy of 6 years. So you can see that generational gap for the same phenomena. So Ferenc Krause was working with another type of experiment, and one that made it possible to isolate a single light pulse that lasted 650 attoseconds. So both experimental pedagogies, differences, whatever they were. So what was happening? The laser light is transmitted through a gas. Ultraviolet overtones arise from the atoms in the gas. In the right conditions, these overtones may be in phase. When their cycles coincide, concentrated attosecond pulses are formed. Now, this is the wave theory we all study in our secondary physics, that overtones are superimposed. Now, just see this one, this one, this one. When they are all superimposing, so they reinforce or cancel each other. This is the phenomena of the light, of the waveforms, what we have been understanding. So reinforce or cancel each other. And so this is how we get the attosecond pulse. Series of overtones when they are superimposed. So Pierre Augustini and his research group in France succeeded in producing and investigating a series of consecutive light pulses like a train with carriages. They used a special trick, putting the pulse train together with a delayed part of the original laser pulse, like a Morse code sending things out there, to see how the overtones were in phase with each other. So phase and non-phase, that's the waveform. I think that's basic physics we all understand. So this procedure also gave them a measurement for the duration of the pulses in the train. And they could see that each pulse lasted just 250 attoseconds. So they actually produced this. And this was the experimental setup, laser light, gas filter, combined beam. So further deeper into it, the Nobel Prize has an elaborate scientific documentation for those who are really interested to go. So the laser light is divided into two beams. When one is used to create a train of attosecond pulses, this pulse train is then added to the original laser pulse, and the combination is used to perform extremely rapid experiments. So laser light, it goes here, it gets reflected, it goes through a pulse train, through a gas, a pulse train is created. And the same laser light with some delay, it matches here, and this combined beam, and then the observation is done out here. So this is the train of pulses. So Ferenc Krauss and his research group in Austria, they were working on a technique that could select a single pulse, like a carriage being uncoupled from a train, and switch to another track. So there's a difference, a distinction between the two. The pulse they succeeded in isolating lasted 650 attoseconds, and the group used it to track and study a process in which electrons were pulled away from their atoms. And these experiments combined, they have demonstrated that attosecond pulses could be observed and measured. So this is in its infancy, this scientific discovery, but then it's a breakthrough any which ways. And these pulses, they can be used in new experiments. Now that attosecond word has become accessible, कहते हैं ना सूक्ष्म प्रकृति आज विज्ञान को प्राप्त हो गई, सूक्ष्मतम attosecond level knowledge. Tomorrow is space day, as I started with the light year and attoseconds. So just see the two dimensions of time. And so these short bursts of light can be used to study the movement of electrons. It is now possible to produce pulses down to just a few dozen attoseconds, and this technology is developing all the while, like the mRNA nucleoside base technology, which was championed in around 2010, 13 or so. It came as a rescue for the humanity at large against the COVID-19 virus, as we all know it in the colloquial term. The mRNA vaccines, the effective ones, speedily could be developed without undergoing the cumbersome process of cell culture. So these attosecond pulses, through this phenomena of overtones, passing an infrared laser light through a Nobel gas, and like maintaining the phases, cancelling them out, creating an attosecond pulse. So this is a kind of a very subtle technique. So electrons movements have now become accessible. कैसे जो इलेक्ट्रॉन है दौड़ लगा रहा है, कैसे घूम रहा है, कैसे नृत्य कर रहा है, वह वैज्ञानिकों को आज through these attosecond pulses we can plot it, measure it, understand it. The way scientists have created a mega telescope to go to the center of galaxy. A couple of years back, the Nobel Prize in Physics was given to that mega scale Nobel phenomena of that ultra gigantic telescope going to the center of the Milky Way, the God particle we all call about it, the center of it all. So now this is a subatomic level of the same complexity. So attosecond pulses make it possible to measure the time it takes for an electron to be tugged away from an atom and to examine utne time ke liye, because the pulse is of the same order, the electron is going for a small excursion and returning back. Like classroom teacher, if it is teaching and you go from one bench to the other quickly and return back. So this is the kind of phenomena, the mischief which electron is doing. So, and to examine how the time this takes depends on how tightly the electron is bound to the atom's nucleus. Like the Earth's gravity, it keeps the atmosphere and the larger phenomena towards it. So how the atomic nucleus binds strongly the electron. So these phenomena, this is the next level subatomic physics which would be coming because of these attosecond pulses with us. Now it is possible to reconstruct how the distribution of electron oscillates from side to side or place to place in molecules. There are electronic clouds, as we all study in chemistry, largely electrical cloud, because physics is more about the concrete, discrete part. Chemistry is more about the other fields and all that stuff. So previously, their positions could only be measured as an average. Now they can go to a very specific aspect. So attosecond pulses can be used to test the internal processes of matter and to identify different events. These pulses have been used to explore the detailed physics of atoms and molecules, and they have the potential applications in areas from electronics to medicine. Jad se Chaitanya ki or, the entire spectrum would be covered. And for example, attosecond pulses can be used to push molecules which emit a measurable signal. And the signal from the molecules has a special structure, a type of a fingerprint that reveals what molecule it is. And the possible applications of this include, again, medical diagnostics, perhaps biopsy, perhaps the various, you can imagine, and so many things might be happening because of this attosecond pulses. I will now request Dr. Surbhi to culminate it, because even the Nobel paper, the press release has culminated with the application of attosecond pulses for medical diagnostics. So
diagnostics, is a very important from the point of view that accurate diagnosis. When we say accurate diagnosis, the element of pulses, the element of time motion studies become important. So say, for example, when we are doing, maybe a kind of a karyotyping or some kind of a study where we're using the diagnostic machines, in which, like, say, for example, as said, maybe an analysis of a post-mortem specimen, in which DNA studies have to be done. So, light amplification. And so these are the areas in which the attosecond pulses concept can be taken into consideration. I would
so
say
who
that.
had known when Tesla was inventing his phenomena, he was perhaps not knowing that this whole physical phenomena would be used in something called magnetic resonance imaging, which has become quite an important aspect. When the Doppler effect, the color Doppler, the ultrasound phenomena, what we studied, that the professor forgot at what speed I was traveling, the famous joke. But then it is the central stay of all diagnostics, especially in the pregnant women. The health of the fetus through those, I would say,
monitors,
innocuous sound waves you are creating in imagery. So physics really has a phenomenal application for the welfare of the human body, the diagnostics part of it. So with this, we come to the close of this Know the Nobles Forum, the physics laureates for the year 2023. And we try to explain, we try to understand ourselves, because these are decades and decades of physical phenomena in physics is best understood in the laboratory when you do your own vernier calipers, you do your own bench experiments and all. So here we saw that how a theoretical foundation of overtones culminated into a kind of experiment which was set up by the two different aged Nobel laureates, as we saw. And they really experimentally produced over there. And it would be having inordinate, the greatest benefit to mankind in years to come. We will be seeing these attosecond pulses coming to a host of applications in times to come. So we thank you for being with us in this Know the Nobels forum. And do visit, do register for the Know the Nobels contest. The quiz for it, you have to choose one field, be it medicine, be it physics, be it chemistry, any of the 6 Nobel dimensions. And there would be a very intricate quiz, a contest on 3rd of December, which is a Sunday, based on these Know the Nobel forums, the Nobel personalities, the Nobel phenomena. And on 10th of December, which is the Nobel Day, when all these Nobel laureates will be celebrated, will be felicitated in Sweden, Stockholm largely, and Nobel Peace Prize goes to Oslo. That has been the tradition. The same, I would say, Nobel connoisseurs, the young Nobel connoisseurs, we will be felicitating them as well, based on their performance in this, because the whole idea is to absorb this frontier of scientific discoveries and scientific experimentations, and then mapping it with what you are studying. It is somewhere a feedback mechanism, a kind of what even the Nobel laureates did, using the same pulse with a delayed impact and creating a train of short pulses out there. So with this, we come to the close, and we will be meeting again tomorrow, 9 p.m. For the Nobel in chemistry, which will be announced tomorrow, 4th of October. So till then, namaste.